So today's speaker is Colin Triplett, and he's an assistant research physicist at the Space Science Lab at the University of California in Berkeley. And he joined SSL in 2016 as a postdoc to work on the ICON project. Since then, he has worked closely with the Science Operations Center for ICON on low-level data products and doing data analysis on the MIGHTY data. He earned his PhD in 2016 from University of Alaska Fairbanks, working on LIDAR and rocket studies of turbulence in the mesosphere and lower thermosphere. And today he's going to present on small-scale waves in the volume emission rate and wind products of the ICON MIGHTY instrument. So go ahead, Colin.
All right. Thank you so much, Nick. And everyone who puts together the HAO Colloquium, I just want to thank you for inviting me to give this talk. So yeah. I'll be presenting on some small-scale waves that we've been seeing in the volume emission rates and the wind products of the ICON and MIGHTY instruments. So just an overview of the talk. I'll give a brief overview of ICON itself, since this is a more public talk. If people haven't heard of ICON or what it can do or what it does, I'll just go through the very basics of it as sort of a publicity. This is what we do. These are our data. You can go and use them, and please do so. And then I'll be giving an example of the MIGHTY VER that we see and the zonal winds, and then sort of how we've been processing those volume emission rates and zonal winds to sort of get out these smaller scale waves that we've been seeing. And then finally, I'll show basically a week's worth of these small scale waves and sort of some histograms of what we've been seeing when you sort of look at longer trends within these waves. So ICON is a single satellite that was launched just over 2 years ago. 2 years ago, 2 days ago. And we are in a 27-degree inclination, 600-kilometer circular orbit. So ICON very much focuses on the equatorial region as well as the mid-latitudes. Most of our instruments face northward, and we can get information between minus 12 degrees latitude to about plus 42 degrees. And there are 4 instruments on board. Those are an EUV imager, an FUV imager, MIGHTY, which is comprised of 2 separate instruments, A and B. Those 3 are all remote sensing instruments. So the EUV and the FUV use UV air glow layers to get composition. MIGHTY has the 2 MIGHTYs that use red and green air glow layers to get wind and temperature information. And then we have an in situ instrument, an ion velocity meter, the IVM. There's 2 of those on board. Only one of those works at a time. So basically IVM faces the RAM direction and gets us in situ ion measurements. The reason we have 2 is ICON has the capability of looking northward, which is what our standard look is. We can also turn around and look southward. So we have an IVM-B in order to look in RAM while we're looking southward. So this is just a nice diagram that was put together by Goddard many years ago now. This sort of demonstrates a picture of ICON, what it looks like. And here we see at the bottom the in situ IVM that's giving us ion velocity, ion density, and other measurements of the ionosphere as we fly. And then you have our three remote sensing instruments I talked about. MIGHTY, which uses these red and green line air glow layers that we can see to get neutral winds, as well as the infrared that gives us temperatures. And then again, the FUV and EUV using their UV air glow layers to get composition and ion abundance close to where the winds are located and the temperatures are located. So this is the platform that we have. These are the data that we put together. This is also a very old diagram that I'm sure some of you have seen before that just lists all the different data products that we produce. Again, the 4 instruments on board. The products that you see that are highlighted in black are products that are currently available on our website, either through an anonymous FTP at the Space Sciences Laboratory itself, or through SPDF. So we have basically calibrated brightnesses, and then we have more of the geophysical data here. These are all the level 2 data. So if you ever are talking to someone who's working with ICON data, they'll generally talk about level 2 data and based on their numbers too, especially if you're within the team. And basically, I'll be focusing on just one data product today. These are the cardinal wind vectors, the level 2.2 data. These here in red are products that are being currently worked on and will soon be available within the SDC itself, so at that FTP site. And these are model output data that use ICON data to force models either from boundary conditions or whatnot in order to give us global views of what we believe the ICON data are telling us. But again, I'll just be focusing on a single data product today, these cardinal winds that we get out of the MIGHTY. This is just an example of a singular orbit. So at the start of this, this is where ICON was located. It was located here, just outside the Caribbean. You see these green and this orange and red line, as well as the squares. The orange and red are either the MIGHTY, where MIGHTY A was looking, or MIGHTY B was looking. Then you have the EUV and the FUV, which look basically in the same direction. And these are the tracks for the next orbit that is currently happening right above our heads. So actually through this entire conversation, or this entire meeting, we will be sampling over Boulder itself. So this just gives us an example of also sort of what the tracks look like as we fly through the day and night. And I'll come to why that's important later, but just keep in mind sort of the scope when I talk about an entire day side or entire night side, and sort of see how MIGHTY A and MIGHTY B are located. So because I'm focusing on the level 2.2 products, just sort of an overview of MIGHTY itself. So MIGHTY is the Michelson interferometer that looks at the thermosphere using the air glow layers in order to get the temperature and neutral winds out of it. It's comprised of two instruments, like I said. One, MIGHTY A, is looking ahead at 45 degrees from RAM. One is looking behind at 135 degrees. So they're 90 degrees apart. Basically, the wind measurements use emissions from the green line and the red line to measure between 90 and 300 kilometers. So basically, MIGHTY A looks at the red and green line that's coming in, and actually looks at the Doppler shift of that line to figure out the speed at which those air parcels are moving. And MIGHTY B does the same, and since they're 90 degrees apart, we can actually pull out vector information to see what the cardinal winds are doing. And that's what the level 2.2 product is. We also have those line of sight products, which are the level 2.1s. Temperature is measured using the 762 nanometer band of the O2 emission. All these products are currently available. The data I'll be showing today are currently available, sitting on our site for anyone to use. And an important fact to remember is that during the daytime, MIGHTY integrates over 30 seconds, and during nighttime, it's integrated over 60 seconds. So again, for this presentation, I'll be focusing on just on the green line, between 90 and 160 kilometers, where the best data is located. I'm also only focusing on daytime data. So I'm looking at a very, very small subset of even just the MIGHTY data itself, and even a smaller subset of the entire ICON data set. So there's a lot of different things that we can do with ICON, and I'm basically just presenting something that has sort of appeared out of the data that we really weren't expecting to see. So when you talk about volume emission rate, it's basically looking at the glow that's coming from the air glow layers. And this is sort of what you'd expect to look for the green line. You have these sort of two peaks, this bottom peak, between 90 and 110. Then you have this sort of secondary peak sitting around 135. MIGHTY sees both of these peaks pretty much all the time, and we would sort of expect them to be nice and smooth, peaking around solar local noon. So on the bottom here, we're going from 8 to 5 solar local time. So if you remember that plot of ICON flying that I showed you, and that entire day side. So this is that entire day side pass or this would be an entire day side pass. So starting from 8 and 17, this avoids the terminators. MIGHTY can have some issues at the terminators based upon whether or not there are issues with SNR or issues with how the volume emission rates look between A and B. There's whole different things, and there's a lot of documentation that explains that to you. But I basically focused on the best of the best data. And we sort of expect it to look like this. Kind of smooth, has this nice shape, peaks around noontime, wherever we're sampling noon. But when data started coming down in January of 2020, we started noticing some interesting things. These is what we started actually seeing. So here we have 3 consecutive orbits number 1, or 3, 4, and 5, for January 1st of 2020. So this is some of the first data we actually came down from the satellite and was processed out to level 2.2. I should mention these VERs are reconstructed from the MIGHTY data itself, because it's an interferometer. Because of how it samples, we don't actually get to like a snapshot of the VER. We get how it interferes with itself, but these are reconstructed from that. I will also point out the VERs are not absolutely calibrated. They haven't been calibrated to ground truth. So these numbers are good, but don't say something like, oh, this peak here is like 650 is exactly 650. But for what I'm doing today, that doesn't really matter as much. So anyway, we started noticing that the VER layers had a lot of dynamics going through them. As you can see, these striations that exist in the orbit number 3, we see very similar striations in number 4 and number 5. They seem to be consistent between the orbits. And we want to understand what's going on here within the VER. We expect it to be nice and smooth, but it's not nice and smooth, and ICON doesn't see them nice and smooth. So when we start looking at the wind data itself, so this is just the zonal wind, so this is the east-west wind, compared to the same exact orbits, these are those data that come out. And even though there's also sort of a large-scale wind flow going on, we see similar structures within the wind that seems to correspond to structures within the VER. It's a little harder to pick out because of that underlining the baseline wind structures, but we can see that they seem to line up. Again, we sort of see this in the number 4, and we see these other larger structures in number 5. And we see these all the time. When we look at pretty much a day, we see them most of the time during the day. They seem to be consistent, and we want to understand what's going on here. What's the physics that's going on that's affecting the volume emission rates, showing these striations, and then what the winds are telling us about that. So there's some hurdles that need to be overcome when we want to start looking at these smaller scale structures within the volume emission rates and the winds, mainly because, as I showed earlier, the volume emission rate has a very set structure that we expect, sort of a parabolic shape that peaks around noon, and the winds themselves have an underlying mean themselves that we need to subtract away from these orbits in order to get at that smaller scale structure. Also, if you look at some of these data from the previous plot, you see these black holes. This is where data is missing. So the data here is only of the top quality. So there's a flag within the data called wind quality. This is when wind is equal to 1, which is the best of the best data that they have. And so these holes are where the data is either not as trusted in order to get the quality 1 for a whole number of reasons. The data files themselves have another variable that actually explains why each particular point is not given a quality flag of 1. So we see we have these overarching structures, and then we see that they have these holes. So all these things need to be worked on in order to get the processing done correctly. So the first thing to really do is sort of find a mean value for the VER for the day and as well as for the wind in order that so we can subtract that out to try to get to these smaller scale structures. So in order to do that, we take the 15 orbits that we get in a day for the MIGHTY data, and then we just sort of mean them all together. The altitudes within the MIGHTY data are always on the same grid. Excuse me. So that makes it easy to sort of bin things in altitude because they're all on the same grid. And then we bin in local time to about 0.1 hours. Now the reason we do it at such a small amount is basically each point when you go along that x-axis is about 0.1 hours big. So we get a mean of basically each individual pixel for the entire day. And that's what I showed earlier for January 1st to give you that idea of what that mean looks like. So we see that the mean processing works. It looks like we expect it to. There might be some small variations in there, mainly because we're only looking at 15 days and there's all these other small structures underneath, but they seem to be doing well. So then we can subtract the mean for each orbit. And as I said, we only use the best quality data that's coming out of the MIghty. So here's two examples of those means again. I already showed you the mean VER for January 1st. Again, we see that nice sort of smooth structure of the two different peaks. And then sort of the mean winds for the same thing. We see a very strong westward flow within these data. Again, black here means missing data. There's currently an issue with the lowest pixel in MIghty that is currently being fixed. So don't worry about the fact that there's a black bar on the bottom. That doesn't really affect the analysis at all. But we see the larger scale structures, and we see that the mean seems to be working. This is what we kind of expect to come out of a mean when we look at a single day. The other thing to point out, we don't see really the small scale structures that we were looking at individual orbits. So because these are done in local time, so as we fly through the day, we sample at this where the sun is located in different parts above us. Since we don't see those small scale structures existing within these means, we know that these structures aren't locked to a particular local time. So we know that they may or may not, well, we know that they're not locked to particular local times, so these aren't like tides. They aren't locked to the sun in some way. So we have our mean processing. It seems to work. So now we subtract that mean from each orbit, and this is what we get. So these are difference plots now from just particular orbit number 3 again on January 1st for the VER and for the zonal wind. And we see those structures that we saw earlier, but they're much more pronounced. So our mean subtraction seems to be doing well in order to get us these sort of smaller scale structures that sort of move through the image. And they seem to correspond to each other. There seems to be this sort of the structure at about 12 local time in the VER that seems to correspond nicely to a structure maybe at 12 local time in zonal wind. They may not be perfectly aligned, but they seem to have some sort of correspondence to each other. So we now have this two-dimensional grid of these difference plots between each individual orbit, and we want to now try to pull out whatever information we can on these smaller scale structures, on these peaks that we're seeing. So in order to do that, this has gone through many different iterations. Some of you may have seen this work presented at AGU and some other conferences. So we've had to go through different iterations because of data issues, how things have been changed within the data set, how we want to look at different things. And basically, so far we found sort of the best way to do this is to go by altitude. And as I said, each altitude is on a common grid. So we can basically take a slice from each orbit, or each of those difference plots, and we do sort of a wavelet analysis on it. So we just run it through a wavelet, and we focus that wavelet at particular sizes. So we focus it on between about 200 and 2,000 kilometers, and 0.1 to 0.8 hours in local time. Now, as some of you probably figured out, since we are a spacecraft flying, as we sample, that x-axis that gives local time also has a distance component to it. And it's really hard to actually separate those two. So when we are sampling, or when we're looking for these peaks, in both local time, we're also looking at them in sort of distance and size. And we assume that these structures are frozen in as we fly. We're assuming that as ICON is flying, these structures aren't moving so quickly that ICON is sort of blurring them as it's being sampled. So we have to have this idea of both space and time within sort of this wavelet analysis. So that's sort of why I'm giving both units here in order to understand what these structures are. So basically, we run each altitude by altitude with this wavelet, and it basically finds peaks within those ranges. And then what we'll do is look at each individual profile now of where those peaks are. So before we were moving along sort of moving along individual altitudes, now we're looking sort of vertically And we look to make sure, or we look to see if there's a peak at one altitude, if there's another peak close to it, and then, and that has to be sort of within this 0.4 hours or about 1,000 kilometers. And we want to make sure we keep just ones that are 10 kilometers. This is sort of arbitrarily chosen through some trial and error to sort of get these structures that we're seeing. But we assume, because each altitude is independent of each other, and since our mean was processed in such a way that we're not really blending those pixels together, that if there's a peak at one altitude and there's another peak that's close to it in the next altitude, that they're part of the same structure. So that's sort of the idea of how we're getting rid of sort of the noise within this peak analysis and sort of keeping the actual data there. And we just set that around 10 kilometers. And then within that 0.4 hours, not only do we look for whether or not there's a 10-kilometer extent, if they're within that sort of 0.4 hours, we make sure that they're part of the same group. We just assume that it's the same wave within both the VER and within the wind. So this is sort of how we're starting to pull out the information from these waves that we're seeing within the data. So when we do that, it's just another example of it. From, again, the VER on the left and the zonal wind on the right. These little x's that you see are peaks that were found by the algorithm. And then the stars are the peaks as well, but meet all the other criteria that were found. So we're seeing that there are peaks that don't meet the criteria. They're either noise or there's some other spatial scale that we're not interested in. But we do see these long sort of structures that exist in both data sets. There might be these three structures on this particular orbit that line up with each other. The VER might have other structures that aren't showing up in the winds. These sort of discrepancies and agreements between these two are still being looked into as to why. But we see that this algorithm is finding the peaks nicely. And then because we can find these peaks, we can start doing some analysis on them. So if I get rid of all of the x's and only focus on the structures that are really good within these data. Again, this is orbit number 3 of January 1st. So again, the first data that we saw coming down from ICON, we see these structures. I've just changed this color scale to make it so you can see the stars a little bit easier. But these are the structures that are found. And the simplest thing to do is we have a line on a plot is to sort of figure out, well, what's the slope of that line? So we run these through just a normal linear regression, and we get these sort of slopes. Again, the solar local time on the bottom also corresponds to a distance that is traveled. So that's why I'm giving these both slopes in this kilometer per hour and this kilometer per kilometer. These units are a little weird. So just to explain, this is basically saying that for every hour of local time traveled, the wave has moved vertically 25 kilometers, or for every kilometer traveled on the x-axis, it's moved this very small value in vertical. Because you remember, the air glow layers are very, very thin in altitude as compared to what we're showing here. Like these plots are not at the same ratio. If they were at the same ratio, the y-axis would be very, very smushed compared to the x-axis. So when you run this just simple linear regression against these peaks that are found, we see very similar values. Around 25, 20-ish, some get higher, some get lower. And for most of these are eastward, which is what we originally saw within the data, that most of these things seem to be moving from, eastward and upward. So, we saw these, it was sort of confirming what we were agreeing, or confirming what we were seeing earlier. The values seem to correspond to each other. So we know that there's something going on with how these peaks between these two different sets of data are related to each other. So we have this ability to do this with a single orbit. So what happens if we run it for an entire week? So we look at these sort of slopes over an entire week, and this is what we get. This is very much hot off the presses. So if you have questions on this, I might be able to answer them, I might not. But this is just, so for, again, January 1st, 2020 to January 7th, 2020, the histograms for the VERs are in green, the histogram of the winds are in blue. And again, the only difference between these is just whether or not I'm looking at that sort of kilometer per hour local time slope or that kilometer per kilometer slope. But some interesting things sort of arise from this. So first off, I just want to point out both of these histograms have about the same number, but both about 270, but they're not perfectly the same. So we don't find a peak in the wind for every peak in the VER. There seems to be more peaks in the VER than there are in the wind. That could be related to a whole number of things. But that seems to be the case, at least for this week worth of data. This data is comprised of 71 orbits. So if you do the quick math, we should have about 100 orbits for 7 days, but we only have 71. So what we're seeing is the waves, though they exist in quite a few orbits, and most orbits that we see, there are orbits that don't have these. And we're sort of starting to look into locations and other things to see whether or not we can sort of tease out as to why that might be. Again, since we are sort of flying, we have a particular orbit, how we look at different parts of the planet change throughout the year with our precession cycle. So all that sort of complicates looking into some of these different things. And then the bin sizes, just to give you an idea, you know, this is the bin size of 5, and then this 0.002. So each is about a tenth, sort of those major tick marks on the x-axis. So for a week's worth of data, we have a decent amount of, a decent sample size, and sort of the most obvious things appear. When it comes to the VERs, there seems to be sort of this two-peak structure. They both seem to be sitting around maybe this 25, either minus 25 to 25 kilometer per hour area, and it seems to have this two-peak structure. So even though when we were looking at the data, just looking at it, we suspected they were all eastward and very, very few westward, you could see by eye, it seems that that's not necessarily the case. The VERs definitely seem to have more that are in the positive value, so in that eastward sort of tilt, but there definitely seems to be a large percentage of negative. And that is sort of the next step that we're sort of looking at is, okay, well, where are those negatives? Do those negatives correspond to a wind or not? Because again, the wind we see here also sort of has that bimodality, but it doesn't have as skewed eastward versus westward that the VERs have. So that itself might be some sort of indication into the physics that's going on and why we're seeing these within the VERs themselves and not just sort of seeing them within the wind. And then the third thing that's probably most striking is within the winds themselves, we sort of have this third peak that exists around 0 in both, in whatever units you want to look at, which doesn't really exist within the VERs. There's a little bit of it, but it's much lower. So it looks like the algorithm is picking up something within the winds that the VERs aren't showing really at all. So this is sort of where we're at right now. But now because we have these slopes, we can start trying to piece together other actual wave properties of these, to try to pull out things like vertical wavelengths or horizontal like wavelengths, things along those lines, to try to actually piece together what sort of waves we're seeing and sort of the family that they exist. As I said, when we originally started looking, or when we originally were looking at data, we never expected to sort of see these variations themselves, just sort of within the quote unquote raw data, and they were just there. So this is one of the things that sort of ICON has shown us that we weren't expecting. And again, this is just one very small subset of one instrument that ICON has. So within our data, there's a whole rich supply of things to be looking at, whether or not you're a student or a researcher. So these things are there. Please go look for them and find them and let us know when you do. But again, this is sort of where we're at for here. The next steps are obviously to look at longer windows, pull out sort of location information to see whether or not particular days these waves exist in particular regions, or if there's sort of planetary things along those lines, to try to tease out what we're actually being able to sample directly from the mighty data. So with that, I will take any questions.
Thanks, Colin, for interesting talk here. Does anyone have any questions? So Jeff Morrow, go ahead.
Yeah, I was looking at the bin size for, on the left is 5 pixels and on the right is 2.
Mm-hmm.
I would have expected the 2 pixel binning to be more spiky than the 5 pixel binning. You know, because
Right.
the 5 pixel binning would sort of smooth things out. It's primarily only that main peak, but I'm just sort of curious why it's not the other way around. Do you know what I'm driving at?
Yeah, I understand. So the reason that is because of this sort of blending of dimensions as ICON flies. So when you're looking at the sort of the solar local time or actual distance traveled, that the x-axis has a mixture of the two. So basically, there's just a really simple conversion between how many hours of local time Mighty has sampled to how many kilometers that is. And basically, because it's just this really simple conversion between the two, those bin sizes are actually comparable when you look at those units.
Okay,
So
great.
we see about 2,000 kilometers of extent between pixels and between the pixels and Mighty. So they're actually, those two are about the same value when you just sort of compare them in that way.
And I've also noticed that it's also kilometer per kilometer versus kilometer per hour.
Yeah.
Okay, I didn't catch that at the beginning. All right, great, thank you.
Yep.
And then Astrid has a question.
Thanks, Nick. Yeah, thank you very much, Colin, for the nice talk. Do you expect any variation with latitude? I think you're kind of not mixing it together, but not at least considering it at a moment.
Right. So it's pretty simple for us to look at sort of latitude. But since each consecutive orbit, how ICON samples, how to answer this? I think what we're going to see is there are particular sort of events that are being seen here, especially since there are times when we can go orbits without actually seeing any sort of these peaks. So I don't think that's more what latitude we're looking at. It's more just sort of the location on the planet that we're looking at, if that answers your question.
Yeah, okay. Thank you.
And Ruth has a question.
Yes. Relating back to Astrid's question for a moment, I mean, the orbits do have latitudinal progression.
Right.
Okay, so there is some latitude dependence rolled up into this as well, although perhaps more longitudinal than latitudinal.
Right.
Do I have that right?
Yes.
Now, have you ever thought about maybe getting a some kind of experimental run involving gravity wave responses involving these concentric gravity wave responses to deep convection to kind of use as a virtual test bed?
Yes, we've thought about it. We haven't done it yet, but this is definitely that is definitely a good step for trying to understand if these are gravity waves from sort of deep convection or like tertiary gravity wave generation and things like that. A model would be definitely the best way to do that.
The fact that you're seeing positive and negative slopes
Yeah.
would make it seem like you might be in kind of a source region.
Right, that is true. Because we can see, what you'd expect from the concentric rings and how they would be moving. Yes, that's true.
Yeah.
Like I said, the sort of two-peak structure appeared yesterday, so I haven't had a good chance of actually studying the negative slopes, the peaks that have negative slopes, and whether or not they correspond in such a way that it would be a sort of concentric ring structure from like sort of gravity wave generation, or whether or not they exist in a different part of the window I'm sort of looking at.
Thank you.
Gary Swenson, this
Yes.
question.
So, Colin, have you tried to look at the temperatures in the waves in these examples you have?
So the next step is also to bring in meridional winds and temperatures into this, but the analysis code is set up in such a way that that should be straightforward, but I will emphasize should because nothing is ever straightforward with code.
Thank you.
But you're right, bringing in the meridional and temperature products is also a good step too, so we can get a more full view of what at least the neutral atmosphere is doing around these peak structures and how that also might affect how the VER is responding.
Yeah, in fact, temperatures would be a very important thing to look at, and these appear to be very slanted waves, the slow waves. I mean, from the slopes you have, which we've seen on LiDAR data in the lower altitudes, but it'd be interesting that you have these. It looks like these are the same type of things you're seeing in the E region.
Yeah.
And they're bimodal, by the way. We see periods of an hour and 10 hours, almost tidal-like, but they're just very long horizontal wavelength gravity waves. Thank you.
Yep. Guiping has a question.
Yes. So Colin, so are these from the green line? Is that right?
Can you say that again?
Oh, I mean, the winds and the volume emission rates are from the green line. Not. Have you looked at the red line?
So I have not. Very early on, we tried to look at the red line, but that was a few versions of the data ago, and it was far too noisy to really pick things up as much. The newer version would probably be easier to do, but I haven't looked at it yet. We do have a graduate student who's working with the ICON team at Berkeley, who is looking at waves within the red line in a very different way. So the red line will be thoroughly investigated for these as well.
Okay, thanks.
Yep.
Are there any final questions for Colin? If not, then thank you again, Colin, for a great presentation.
All right. Thank you for having me.